Okay. Thank you, Arno, for this presentation, and I also thank you to all the organizers, Flora, Francesca, and also to all the participants. So I'm going to discuss a topic on dynamical systems. So harmony and chaos. So I will try to explain how, in general, they coexist in quite general dynamical systems coming from physics, more precisely from mechanics. So maybe as an introduction, I will first define more or less what I have in mind with these words harmony. So here, harmony is in the sense of the Greek philosophy, more or less, more precisely the Pythagorean school. So this is related to rational numbers, celestial mechanics, let's say at that time, periodicity, and these kind of things. So for the school of Pythagoras, so the motions of celestial bodies were supposed to be very harmonic in the sense that they should share the same ratios as musical tones. And so basically for the Greeks, at least for this school, so they had the whole cosmogony, so a vision of the universe, and through astronomy at some point. And also they wanted to unify this with music, geometry, with the logos, basically. So basically, and this is, this, okay. And so this has to do also in the Greek vision to rational numbers. For Greeks, numbers were rational numbers, which means quotients of two integer numbers. So integer numbers 0, 1, 2, 3, 4, and so on. And so, of course, musical tones share this rational logic. So for example, when you hear a sound of a frequency f, so basically you will more or less hear the same note when you hear f, 2f, or f divided by 2. So this is the octave. On the other hand, if you take ratios as 3/2, 3/2, 5/4, and so on, so you've got also something which is harmonious. And more generally, if you take rational numbers, so what you hear sounds more or less like something harmonious. So you've got harmony, so something which is nice for the mind, basically, has to do to some extent with rational numbers. So this is for music, and for also, as they believed, for celestial motions. So just a word, so these rational numbers, so they are also related to the notion of periodic motion. So a motion is periodic, or a function is periodic, or whatever. Let me put here. Voilà. If it is periodic in time, so it repeats. So for example, if t is the period of f, so f of t plus big T is equal to f of t. And of course, if you put 2t, 3t, 4t, and so on, you will always see the same thing. And of course, motions, so it was not completely clear, but motions of the planets around the sun, so if we share the heliocentric system, so these are periodic motions in first approximation. Of course, when you see them from Earth, they are not periodic, but they are almost periodic. They are quasi-periodic, more precisely. And so I will define the notion of quasi-periodic motion as the composition of a finite number of periodic motions. So here I put finite number of periodic motion as opposed to almost periodic. So we will be mostly interested in quasi-periodic. So finite number of periodic motions. So for example, to simplify, so basically you can imagine that f is the sum of n periodic functions, and each function has its own period, big T I. Okay, so just this. And so here we are in the world of rational numbers, basically. Huh? So we are talking about celestial mechanics. So it's, of course, we are obliged to talk about Newton, basically. So this is maybe make a jump of something like 700 years. And so we have, so Newton, I remind you, so he made many exceptional contributions to humanity. Yeah? So the first one is the fundamental law of dynamics, which is basically a quantitative version of Galileo's principle. Huh? So, which is the following: if you have, of course, my formula is wrong. So it should be d over dt and not d2t over dt2. But okay, so the derivative of the impulsion with respect to time is equal to the force acting on the body. So this is the first law. The second law, which is more, gives us the shape of this F as far as gravitation is involved. And so he discovered also the law of gravitation. And basically, he also developed mathematical tools. And basically, he developed the theory of differential equations. So you've got this. So here in our case, so R is the position, V is the speed. So you've got a differential equation involving position, speed through the force. And so this equation, this differential looks like this. And you know that when you've got differential equation, once you are given initial conditions, so once you specify the position and the speed of the particle at some time t, then with fairly reasonable assumptions, you've got a unique solution. So it's not completely clear that the solution will be defined for all t, and so in fact, it's not the case, but let's assume it's the case. So if you've got this differential equation, so basically let's assume that you can solve it to simplify for every t, and the solution is unique. So now, once you have this, you can understand, and so that's what of the great contribution by Newton, one of the great contributions. So he gave a complete solution to the two-body problem. So basically, we've got two massive bodies that attract themselves through the law of gravitation, and then you can describe their motion. And so, for example, so I'm just going to take a simpler situation. So it's exactly the same. So basically, you've got a big sun, so basically a fixed body, and another small planets turning around this big sun. And so you know that the motion is completely classified. Huh? So you've got either elliptic motions, so the planet describes around the sun an ellipse, and the trajectory, the motion is periodic, and you can compute, in fact, this period depending on the initial conditions. So basically, that's what happens when the Earth evolves around the sun. So you can have this kind of motions. You can have also hyperbolic motions. Then the trajectory of the planet is a hyperbola, so it's an unbounded motion. So this is typically the motion of comets, of some comets that we can see from time to time. And so we've got a limit case, which is the parabolic case. So you can have also parabolas. Huh? So here, which is very striking, is that all these motions are conics, which is also a Greek invention by Apollonius. And so, and the sun is one of the, so in general, in the elliptic and hyperbolic case, you've got two foci. And so the sun is always at one of the foci of these conics. Yeah? So by the way, you see that Newton recovered So what Newton discovered would have really pleased the Greeks, the ancient Greeks. And so because it fits so well with the Greek cosmogony, everything is there. Yeah? So you've got the conics, you've got the periodicity, so it's very nice. Okay, so that's for one thing. Then I'm just going to be a little bit more precise. So you see, so Newton's theorem is really remarkable, in fact, because so you've got these periodic motions around the Earth, at least for the two-body problem. Of course, if you add more bodies, it's more complicated because you have to take into account the interactions between the planets, basically. And so it's not so clear that it's not true, that the motion will remain periodic, even quasi-periodic. But no, this is another story. I will come back to this later. The point is that, in fact, so the Newton's law of mechanics, in fact, they indicate that in many situations you should have periodic motions or quasi-periodic motions. So I'm going to take very simple examples. They are very simple, but in fact they are very relevant in physics and in math also. And so, for example, so the simplest example is that the example of a mass related to a spring. So the equations of motions are linear differential equations of the second order of this form. So let's say x is the position of the mass, and so omega square. I'm not so I forgot to put the formula, but it's not difficult to relate it to the mass and the strength of the spring, basically. And so you've got this kind of differential equation. And so it's a linear differential equation. Omega squared is constant. And so this equation has all solutions of this equation are T-periodic. So basically it means that you can write them, you can write X as a composition of cosine and sinus. Right? It's a sum of cosine omega T and sinus omega T. And so the period is 2 pi divided by omega. And so this is the simplest example. And in fact, it's a really relevant example. So you can also consider n masses related between themselves by springs. And you will have similar equations in a bigger space, a higher dimensional space. And the solutions will still be will be, in that case, quasi-periodic. So they will not be periodic, but quasi-periodic. So basically, there would be sums of cosines and sines. But here you will have different frequency omega j, different periods. So in general, this omega, which is the collection of omega 1, omega n, is called the frequency vector. So just a word, so it's this situation, in fact, is very common in dynamics. So I have considered masses related between themselves by springs, but basically, if you take a general, even very high dimensional systems, when you are close, when the system is close to its equilibrium position, basically, as a first approximation, you will have equations, similar equation and similar phenomena. Of course, it's only approximate. So let me say some remark about quasi-periodicity. Basically, there are two cases. So I have introduced the frequency vector omega, and then you've got two cases. Either the frequencies omega 1, omega n are commensurate, so which means that basically they are related by a relation of this form, n1 omega 1 plus n2 omega 2 plus nn omega n is equal to 0, where the nj are integers. Or this is not the case, and in that case the motion is periodic. Or this is not the case, so you don't have relations like that, except of course if all the ni are equal to 0. So, and you say that then the frequencies are not commensurate, and then the motion is quasi-periodic. So then you cannot see periodicity. what you can see is approximate periodicity. So you can there is a statement for this. I'm not going to give it, but so the system is not periodic. But what you can say at least is that the system comes back arbitrarily close to its initial position infinitely many times. And in fact, it's stronger than this. But I'm not going to talk about this. And so basically, you've got this. And so at least, so as I have said, at least in first approximation, many systems can be seen. You will imagine that they will display quasi-periodic motion. Of course, it's a very difficult statement in general to prove. So it's not at all obvious. But let's say from a heuristical point of view, if you take a system which is close to the equilibrium, you can think maybe that you will have quasi-periodic motions, maybe periodic motions also. And so this is the point. So now I'm going to explore a little bit more the consequences of this Newton equation. So and I'm going to remind the Laplace, I call it a Laplace paradox. I don't know if it's a paradox for Laplace, but so Newton's paradigm leads to strong determinism, because you have differential equations. Once you know the initial condition, in principle, the evolution of the system is completely determined. And so this was basically Laplace observation. I don't know if I have to read it in French or try to translate it in English. So maybe in French first. So, une intelligence qui à un instant donné connaîtrait toutes les forces dont la nature est animée et la situation respective des êtres qui la composent, si d'ailleurs elle était suffisamment vaste pour soumettre ces données à l'analyse, embrasserait dans la même formule les mouvements des plus grands corps de l'univers et ceux du plus léger atome. Rien ne serait incertain pour elle et l'avenir comme le passé serait présent à ses yeux. And so you see, so if at some point you know all the initial conditions, so speed and position of all the particles in the universe, of course, you know the evolution of the universe. So, which basically says that no ontological freedom is possible. Yes, so it's a highly philosophical statement. So this is Laplace, and of course, in Laplace, you see that, so there is this sentence, si d'ailleurs elle était suffisamment vaste pour soumettre ces données à l'analyse. So of course, if you want to describe the position of the universe, you have to know with exact precision of these positions and speed. So which is not the case. Huh? So our inability to predict things comes from the lack of information or precision. So you cannot know with arbitrarily high precisions all the position and motions of these particles. So that's why when you have, in the common sense, chaotic things, though this is due to this lack of informations. And still, you know that probability theory gives a framework to the description of this random phenomena. And so you've got basically statistical laws to understand this. And so this is, so to put it simply, so probability theory provides laws that give statistical grasp on this random common life phenomena. So of course, this is very efficient. It's very efficient, and you've got a theory. So the only drawback of the probabilistic approach is that at some point you always make an implicit assumption. So whenever you make probability, at some point you assume more or less that you got somewhere at a very deep and hidden level, you've got the existence of elementary independent random variables. And then with these elementary random variables, so let's say this fundamental randomness, you can express all the other random variables in terms of them. So this is basically the assumption that you have. So it's very efficient. It's a very nice theory, and you can produce many striking results. But you've got always this little drawback somewhere. And of course, mathematicians try to free themselves from this assumption. But still, so this is very efficient, in particular in statistical mechanics. So what I have in mind is just the motion of n rigid balls in a box, for example, experiencing elastic reflections. And so if you make a suitable statistical independence assumption, you can derive many laws from physics in particular. So Maxwell law, Boltzmann law, Maxwell-Boltzmann law. You can define the notion of entropy. So Boltzmann introduced this. So he pointed out the importance also of the ergodic hypothesis. So which is basically, if you've got such a big system, the spatial and temporal averages should coincide. Okay, so this is what I wanted to say about basically harmony in the Greek sense, and chance or chaos or unpredictability and things like that. So maybe I'm just going to pause a little bit in dynamical systems. I'm just going to recall various notions of dynamical systems. So, because we are talking about dynamical systems, evolutions of systems with time. So more generally, dynamics is the action of a group on a set X, and this is the mathematical definition. So basically, the most common action is the action of R. So, and then you are dealing with continuous time dynamics, and basically these are differential equations. So you have a differential equation like that. So here, y is a vector in a d-dimensional space, in a high-dimensional space. You take these differential equations, and the dynamics is the evolution of the solution with time, and the evolution is given by this phi t. So evolution is with t, and so this is the flow of the differential equations. This is the flow, and this is the dynamics. This is where you've got the action of R. You can also consider discrete time dynamics. So it's it means that you just consider evolution at integer times. And so you can also formulate the same thing by saying, okay, I'm just going to take a set. So this is the most general formulation. You take a set X, a map F from X to X, and then you look at the iterates of F acting on X. So you take X, f of X, f of f of X, f of f of f of X n times. I'm going to call this Fn of X. And it's not a power, it's a power for composition. So this is discrete time dynamics. You can also, I won't do that, but you can also, of course, consider other groups, SL2R, SL2Z, SL3R, SL3Z, so whatever, symplectic groups. And then you've got more general dynamics. A crucial notion in dynamical system is the notion of orbit. So in the discrete case, this is just, you take a point X and you just look at X, the set X, f of X, f of f of X, and so on. You can also look at orbits in a negative time. So this is the fundamental notion. So other fundamental notions, so there are two very important notions, which is the notion of ergodicity and entropy. I'm going to review some other ones. So basically, when you've got a dynamical system, so you take a map F from X to X, I'm going to stick to the discrete time dynamics. It's I would say a fundamental one. So we've got the notion of periodic orbit. So we have already met this notion. So basically you say that a point is periodic if after some iteration it comes back to itself. Fn of X is equal to X. Just, voilà. Okay. Now you've got the notion of recurrence. So you say that the dynamics, or that the point x is recurrent if the iterates of x, the orbit of x, comes arbitrarily close, so often of x, comes arbitrarily close to x infinitely many times. So you have a point. So x, f of x, you iterate, and then you will come back not to x, but very close to x, and then you leave, you do something else, and then you come back to x, and then again, and these kind of things. So this is the notion of recurrence. Voilà. Another notion is the notion of ergodicity. So ergodicity is a different notion. So basically, it says the following thing. So I'm going to read the definition first. So if A is a region of the space X, then almost every point of X in X will visit A infinitely many times. And the proportion of time you will spend in A is proportional to the size of A. So which means basically the following thing. So we take a space X. So this is X. We've got a map acting from X to X. And we have here a region A. And then I take at random a point X, and I look at its iterates, f of x, and so on. And then from time to time, I will enter in A, then I will leave. I will do something, and then I will come back to A, I will leave, and so on. And so basically the point is that you come back to A at some asymptotic rates, which depends on the size of A. So basically it tells you that more or less given any 2 points in big X, you can approximately connect them by an orbit. So I'm not going to describe more of this, but this is an important notion. And the last notion is the notion of entropy, so which is a little bit more difficult to explain, but so basically it says the following thing. So you've got your dynamical system. I'm going to try to make a picture. So you've got your dynamical system, and you take a point X and you want to specify its future. So for example, you say, okay, I want a point X such that at time 0, I'm at this place, at time 1, at some other place, time 2, some other place, and let's say up to time 10. So I'm not going to predict all the future, but I want to say, okay, for let's say a future big N equal 10, the evolution, I know the evolution. Then the point is that the set of point X for which you have this specific time evolution has an exponentially small size with respect to N. So this is the entropy. So I can, so maybe here. And so this is the entropy, this size, Mn of x, is exponentially small in terms of N, and H is a number. So it can be positive, it can be 0 also. And so basically, I will say that the system is chaotic if its entropy is positive. I mean, it would be one possible definition. And so basically, if you want to make a picture, yeah, so what you have to imagine is that, so you take boxes, you take X, and in X you specify, you take a partition, and so you want that X be in whatever, let's say 1, f of x in 1 also, and then you want maybe that f2 of x be in 4, and then and so on. Huh? And so let's say maybe let's write to an f10, for example. Is in 2. So you have specified a future. Then basically the set of x satisfying this has measure here. Of course, I assume that 10 is big, something like that. And so, in fact, what you have to see is that you have decomposition of the space by cells, and the size of each cell is very small. Voilà. So this is the notion of entropy. Bon. Okay, so I come back now to Boltzmann, so statistical mechanics, this kind of thing. So the point is that, so can you prove the ergodic theorem, the ergodic assumption for the rigid ball model? And so I remind you, so you've got in a box, let's say a cube or whatever, you've got n balls. N can be very big, basically it's the Avogadro number. And so they just, the interaction between themselves is just by elastic reflections on the walls also. And so basically you want to prove, can I say something about the system? Can I prove ergodicity? So can I establish Boltzmann ergodicity? And it's a weaker version of positive entropy of the system, but still it would be nice. And it's a very difficult problem. In fact, more or less it was solved, not completely, but at least there was a major progress in 1999 by Domokos and Nandor Shimani, and they proved the result for generic masses. So maybe they are not exactly, don't have exactly the same masses, but if you assume that they are in a generic set, this is true. And it's not at all trivial. And the key model, the key point to prove this is to use the notion of CY billiards that were basically introduced in the 70s, I guess. And the philosophy of signal billiards is that if you take n balls in a periodic box, this is equivalent to the motion of 1 point in a high dimensional box with scatterers. So basically you take, I'm going to give the example with 2. And in fact, this is Sinai model. So here I've got the box, and here I've got my 2 disks. I assume that I'm in dimension 2. And so more or less, this is equivalent to the motion. Now, there are 2 ways to see this. So the picture means the following. So here, what is supposed to be here in dotted points, this is supposed, you can view this either as a square or as a torus. You reflect periodically the things. And here I put a scatterer. And here I've got a material point. I mean, really a point, not a 2-dimensional object. And I look at its motion. So it goes like that. Then you've got a reflection. So, and then here you are on a torus. So you come back here. Then you go here, reflection, you go here. You're in a torus, you come here, and so on. Equivalently, I could have put a picture, a periodic picture, which would be the following. So basically, I take the plane. In each cell, I put a scatterer. Periodically periodically put, and then I look at the motion of my particle. It goes there, then it will go. Well, it's not a good trajectory, so I take a trajectory like that. It goes there, and it goes here, then it goes here. Maybe it will go like that, and so on. Voilà, this is the notion of linear billiards. And so CY did that, in fact, for dimension 2, for two disks. And so more generally, so you can do the same thing if you go high dimension. And so you've got scatterers. So the only thing is that I'm not going to describe the shape of the scatterers. It's a delicate issue. In the CY case, you see the scatterer I had was a disk. So it's a concave, if you view it from the outside, it's a concave body. And so more generally, you can study this linear billiards. So billiards with concave boundaries. So here I really have a box, a concave box, and then I look at things, at the motion like that. And you see here, you've got a high dependence on the initial conditions due to the concavity of the curves. And so the important thing here is that you said that these billiards are hyperbolic. So hyperbolic in the sense that they have this high sensitivity with respect to the initial conditions. So in that case, this is due to the concavity of the boundaries. And I will say, and so you can prove that you've got positive entropy, and I will call this system chaotic. And so the definition of chaos is not completely clear in the dynamical system, but in that talk, I'm going to take positive entropy as a definition. So you can, of course, consider other types of billiards. And it's a very active topic. So in dimension 2, so you imagine a billiard table. So it's a portion, it's an open set in the plane delimited by a curve. And so we've got, of course, the standard billiards when the table is a rectangle or a square. And so it's an easily understood situation. Still, you can have quasi-periodic motions. I can have, so periodic orbits. But I can also have quasi-periodic orbits in that case. If the angle is irrational, I can have motions. Well, my picture cannot be true like that. Well, I will have motions which are like that. So, and I will basically cover the whole square. If I cover, the orbit would be dense in the square. So these are the standard billiards. You have also other type of billiards. So basically, and the motion in general is quasi-periodic. You can have polygonal billiards. So this is a very difficult problem. In fact, so just to tell you the thing is that if you take a triangle, in fact, nobody is able to prove that the motion is ergodic in this triangle. There is one case, so you can prove that you've got recurrence. You can prove that there exists a triangle with which are ergodic, but in general you cannot prove that. In general, I mean for full measure, if you take a set of full measures of triangles, you don't know if they are ergodic or not, and it's a very difficult question. On the other hand, there is a situation which is much better understood, is the situation where the angles of these polygons are rational multiple of 2 pi. Well, I'm not going to discuss this, but it's a very studied type of billiards studied. There are the hyperbolic billiards, so the linear billiards, and there are the elliptic billiards. But basically, that's what we have. And I'm going to focus now on these elliptic billiards. Now, elliptic billiards, basically, I assume that the table of my billiard is a convex. I should avoid lines like that, but I have convex. I've got reflections like that. Huh? So elliptic billiards can be seen as a more general class. So these elliptic billiards, I will concentrate on them because they have the property of having quasi-periodic motions and chaotic motions. And that's why I want to explain. I'm not going to explain it on billiards, on elliptic billiards, but on another class. So basically, in fact, these elliptic billiards are a special class of a more general one, which is the class of area-preserving maps of the annulus. I should add an extra assumption, which is a twist assumption, but I won't do it. But still, it's also area-preserving maps of the annulus are very interesting. And so special class, yeah, so annulus, I'm sorry. So an annulus is something like that, or you can also think of a cylinder. It's the same thing, huh, basically. So basically the product of a circle by an interval or R. Or you can have also this thing. So two equivalent descriptions. You can also even, in fact, have the description of an annulus by the following thing. You just think of the plane. And here you've got, so you take the plane and you take, you look at it. You periodize, let's say, the x variable. It would be the same thing. Okay. Okay, so in that case, so it's a special class of area preserving maps. And in general, they display coexistence of quasi-periodic motions and chaotic ones. And that's what I'm going to explain. In one case, so just let me say that you've got, this is even a very important class of systems in dynamical systems. They include, elliptic billiards, they include the restricted free-body problem, and in fact, that's why they were introduced, basically by Poincaré and by Birkhoff. And so they are very important in celestial mechanics. So at least for the restricted free-body problem, one sun and two planets. You can apply this to the periodically forced pendulum, and this is the case I'm going to study, and you've got also many other applications. So I'm going to explain why you can see a coexistence of harmonic motions, so let's say regular motions, and chaotic motions in this case. And in fact, in that case, so chaotic motions will be positive entropy. It will be also the fact that you can more or less describe it by a sequence of independent random variables. So I'm going to say what is my model. So my model is the pendulum. So you take a point O, so you take a point O, and here you've got a rigid rod, and here you got a mass. So you can normalize the mass, it's 1. And here you've got the gravitational field, G. And so you've got here a pendulum. So the pendulum in general can have this kind of motion, like a pendulum. Even if you throw it fast, it can go like that, and then up, and then down, and then up, and then down, and so on. It can also be still here. It can be still in the up position, but then it's an unstable position. And so you've got all these kind of motions. So basically, you start with this model of the pendulum, and then you make something which is, you take the point O and you force vertical oscillations in a periodic way. And so here is this epsilon A of t is the periodic forcing. And so you've got this kind of equations. So theta second, the second derivative of theta plus omega squared times the sinus of theta is equal to 0. And the omega, the pulsation of the frequency, is equal to, is a t periodic. And you can, is t periodic. Okay, so this is a nonlinear equation. So the linear equation is easier to understand. That's okay. So this is the system you have. And so when you have this, you can write differential equations for the system, which is here, in fact. And just what I just wanted to illustrate here is that, so you will have a differential, so you can write the previous differential equation under this form. And so basically, you can introduce the flow of this differential equation, and I'm going to denote it by phi from 0 to t, and then here there will be some epsilon. And epsilon is if epsilon is equal to 0, the point O doesn't move. And if epsilon is different from 0, it moves periodically. The base point. Now, this map phi is an area preserving map of the annulus or the cylinder. And so that's why this class of pendulums, so the periodically forced pendulum, belongs to the class of area preserving maps of the annulus. So here I'm going to explain how one makes this thing. So the standard pendulum is when epsilon is equal to 0. So then the equation is not difficult to solve. And in fact, if you introduce the energy here, E of the system, you can draw the phase portrait of the system. So here the horizontal axis is the theta axis, vertical axis is the speed, theta dot. And here you've got points. So for example, this point E0 corresponds to the pendulum being at rest. The pendulum is down. Here correspond to the pendulum is up, so the unstable position. These motions correspond to the pendulum is oscillating like that. And these orbits correspond to the pendulum is turning around O. And these blue lines are the separatrix, and they correspond to the fact that the pendulum is up. It makes infinitely many times to leave the unstable position. It goes down, and then it goes up again, and it takes infinitely many times to approach the other position. And so these are these blue motions. So these blue lines are called the separatrix of the pendulum. So this is a nice picture. And so you see that basically all the phase space is foliated by two types of motions. So you've got periodic motions, and you've got the motions on the separatrix. Otherwise, all motions are periodic. They don't have necessarily the same period, but they are all periodic. The fact that there is one further thing here is that, in fact, you've got invariant objects. So the orbits in that case, so the periodic orbits and the separatrix, they foliate the whole phase space by invariant objects. For example, if you start with a point on the separatrix, you will stay on the separatrix. If you start with a point on this ellipse, you will stay forever on the ellipse. Okay, now, and so you can prove that the entropy of the system is 0. So you've got basically 2 points, so which are of interest, so other, but let's say. So these points, the elliptic fixed point, I will call this point the elliptic fixed point, the pendulum is down, and here is the hyperbolic fixed point, the pendulum is up. And so I can describe the dynamics in the neighborhood of each point. So basically in the neighborhood of E, things are just turning. And you can prove that it's really exact. Huh? And in the neighborhood of H, the motion is more difficult. It resembles something which hyperbolic. You've got kinds of hyperbolas. So I'm not going to say more about this. Now I'm going to look at the time T map of my diffeomorph of the flow. So basically, I'm going to make a forcing with period big T. And so the good thing is that when I take my differential equation, when epsilon is equal to 0, I'm going to take photographs of the system each time T. So for example, if I start with a point which is here in red, P0, then when I iterate, so P0 is going to move, and P0 is going to turn P0, P1, P2, P3, and so on. So basically, you've got this point, P0 was here, and you go like that. So you've got a discrete time dynamics. The motion of P is not anymore periodic, but it's quasi-periodic. And so you can describe this. And so here again, you see when epsilon is equal to 0, so when there is no forcing, the dynamics is nice because the whole phase space is covered by invariant objects. So which are basically these lines, the separatrix, and these kind of ellipses. And so all the motions, more or less, except from the separatrix, are quasi-periodic. And so the question is, what happens when you put the forcing? So basically, you can look at this in the neighborhood of the elliptic fixed point, E0, or the hyperbolic one. I'm going to concentrate on the elliptic one. The hyperbolic one is less interesting in that case. What is interesting is the separatrix. So basically, in the neighborhood of the elliptic fixed point, what you can prove is the following remarkable theorem. It's one of the big theorems of the 20th century. Yeah? So it's a major achievement by Kolmogorov, Arnold, and Moser, which led to the building of KEM theory, and which is basically the following. So in the neighborhood of E0, what you can prove is that you have invariant closed curves surrounding E0. People call them invariant circles. These curves, their union do not cover the whole phase space, but a positive measure set. And motions close to E are stable, so they do not escape. And they are quasi-periodic. So the picture is the following. So in the neighborhood of E0, so you can find curves. So here there are these dotted curves. You take a point here, you stay on the curve, you turn at some quasi-periodic rate. I call this speed of rotation a rotation number. You can define what it means. And the point is that these, and here you cover not a whole neighborhood of E0, but at least a set of positive measure. So positive probability measure in some sense. And so the point is that this rotation number, they have some Diophantine properties. People say that they are Diophantine, they are badly approximable by rational numbers. Again, so rational numbers play an important role, but here the curves that are going to survive are the ones that have highly non-rational, in some sense, rational numbers. So Diophantine rotation numbers. And this is the content of the KM theory. And so there is one extra thing. So the theorem holds more or less in high dimension. Just point C is not satisfied in high dimension, which is stability. So if you take a point inside, so for example, here, it cannot escape, it cannot go like that. It cannot escape like this, because it has to stay between the two curves, these two curves. So this is the stability of motion. This is a theorem by Moser. Now, so I have explained that in this situation, I have quasi-periodic motions. So kind of harmonic motions. Oh, this is nice. And now I want to explain why can I get some chaotic things in this situation. And so I'm going to explain the route to chaos. So usually people use this word for other things, but So recall the picture of the standard pendulum. So basically here, this is the phase space of my map phi, my dynamics. So I have a dynamics defined on the annulus or the cylinder. And so when epsilon is equal to 0, I've got this nice picture. The whole phase space is foliated by invariant objects. But we know that this picture is only approximates, because this was for epsilon is equal to 0. Now I'm going to switch on epsilon. And so what happens, and this is again another big discovery, and it was a big discovery by Poincaré. So Poincaré wanted to solve the three-body problem. And so what he discovered is that in general, the separatrices, so these blue objects, they split. And this is the so-called Poincaré-Melnikov splitting. So which means that here in that picture, you've got nice curves, and these are invariant objects. Here, they have to split. So this is an invariant object by the dynamics. This is also an invariant object by the dynamics. But the point is that they do not coincide. Before they were coinciding, but now they do not coincide anymore. And instead, they cut in a transverse way. And this leads to chaos, in fact. In fact, at least it leads to complicated dynamics. And this was the observation by Poincaré, is that once you have this picture, you are obliged to have this one. Now, I'm not going to explain, but basically these objects are stable and unstable manifolds. And so if you have a curve like that, it has to come back and it's going to be expanding. And so you've got this picture. Here is just the beginning. In fact, the picture is much, much more complicated. And so and Poincaré realized that it was a very complicated picture. In fact, here is just an ébauche of the picture. And then if you continue it, it's very difficult. Still, once you have this, you can prove the existence of many periodic points and things like that. There was a second breakthrough by Smale in the 60s, is that once you have this, you can prove the existence of chaotic zones. So really positive topological entropy. So you've got here, you can define, so I'm not going to do that, but so here you can define, in fact, along the separatrice, but let's say here, you can define an object which is called a horseshoe. It's a compact invariant hyperbolic subset of the plane. And this produces chaos. Chaos in the sense of positive entropy. And here I'm cheating a little bit because this is just topological entropy. Still, you have also instability zones, Birkhoff instability zones. So just the thing is that just this splitting of separatrix creates chaos. And that's how chaos comes into the picture. The thing is that, yeah, in fact, you can repeat this picture. So once you have this, what I have proved up to now is that I have proven the existence of quasi-periodic motions and chaotic motions at the same time. In fact, the point is that you can say much more. In fact, you've got a kind of hierarchical structure, and you will have this phenomenon at small scales, arbitrarily small scales. So let's come back to the unperturbed situation. So I have the picture of epsilon is equal to 0. This is the pendulum picture with the nice foliation of the phase space by invariant objects. When I switched on epsilon, so not equal to 0, so the curves I had, so here I have, for example, a curve. So if this curve is Diophantine, in some sense, it's going to survive. But there are curves here that are not Diophantine. They have rational rotation number. When I switch epsilon on, they disappear, in fact. And so the only curves that remain after perturbation are the Diophantine curves. And the other ones that disappear, but not completely. They leave a trace. And so, for example, it's better understood if you have periodic points. If you take a curve which had periodic rotation number, when you switched on epsilon, the curve will disappear, but there will remain periodic points. And these periodic points, there are two types. You've got elliptic periodic points, and you've got hyperbolic periodic points. In the elliptic points, you've got this, the KM picture holds, and you will have quasi-periodic motions. In the other one, we'll have the Poincaré-Smale scenario, and then you will have chaotic zones. And so the general picture is the following. So when you have an elliptic fixed point, it gives rise to another real preserving map, to invariant curves, quasi-periodic ones, and to elliptic and hyperbolic periodic points, and also to a hyperbolic point with a separatrix and a chaotic zone. And so basically what you have is a hierarchical structure of these kind of things. So basically the picture you have is the following. So I took the picture from Wikipedia. The picture should be turned by 90 degrees. And so just here, so does it work here? Yeah, it works. So here you see, for example, so here this is what was an elliptic fixed point. This elliptic fixed point is surrounded by curves, KEM curves, okay? But here you've got something which was a hyperbolic fixed point, and this hyperbolic fixed point had some, will display a splitting of separatrix. So in this zone, we'll have many periodic points. Some of them will be elliptic, some of them will be hyperbolic, and you will have again and again this kind of picture. And so basically, if you zoom, I'm sure that if I'm zooming, for example, let's say here, I will find basically this kind of picture. So basically, I'm almost finished. Just I wanted to quote one thing, so which is the entropy conjecture, and which is the following. So the quasi-periodic zones that we have described, they have positive measure, positive probability. On the other hand, the chaotic zones, the ones we have constructed, they have zero measure. So a question, which is a fundamental question in the subject, is does these chaotic zones, or positive entropy, does it cover a set of positive probability measure in phase space? It's a very difficult question. If you solve this, and if you are less than 40, I guess you've got the fields method. Well, I'm going to stop here. And thank you for your attention, and sorry for the delay.
Thank you. Thank you very much, Raphaël. I think everybody now